Recently, DeepSeek published its paper. We are going to explore how the algorithm behind their latest R1 model works. However, to understand this, we first need to grasp how reinforcement learning through human feedback functions. Finally, we will examine the group policy optimization algorithm, which is the algorithm DeepSeek used to train their recent thinking model, R1. That said, there are some prerequisites for this video. You should have a basic understanding of reinforcement learning. You should also have some knowledge of the proximal policy optimization algorithm, and also transformer architecture in large language models. For a simple overview, I explained the PPO algorithm in my previous video. However, there are many other videos available online on the same topic. You can watch those as well. Now let's get started. Let's first understand how a reward model is trained using human feedback. Consider a simple reinforcement learning agent interacting with its environment. The agent observes the environment. We also use the word state to refer to its observation. Based on that observation, the agent takes an action in the environment. Normally, the agent receives a reward value from the environment after taking an action. But here, we want to train the agent using human feedback. So, how do we design the reward system with human feedback? We simply collect a list of trajectories from the data, which is essentially a collection of states and the actions taken on those states. In the case of LLMs, you can consider the output response of the LLM, where every token generated using the context is an action, and the context itself is the state. The reward model takes an observation-action pair and provides a scalar value as output, which represents the reward for the action taken in that state. But how do we train this reward model? Let's say we have collected two trajectories. Now, we receive feedback on both trajectories from a human. In this case, let's say the human preferred the first trajectory as the better one. We feed each pair in the trajectory to the reward model, and it predicts a scalar reward value for all the pairs in both trajectories. Our goal is to guide the reward model to assign a greater reward to the trajectory preferred by the human. In terms of language models, the answer preferred by the human should receive a greater total reward. In short, we want the total reward given to the trajectory preferred by human feedback to be greater than the trajectory not preferred by human feedback. Initially, we assumed that the first trajectory is preferred by the human, so it should receive a higher reward. For that purpose, we calculate the probability of the total reward for both trajectories using the softmax equation. This involves taking the exponent of the total reward for each trajectory and dividing it by the sum of the exponents of the total reward for both trajectories. Now, if the human preferred the first response, we maximize the probability of the first trajectory using gradient descent. Since both probabilities are dependent, increasing the probability of the first trajectory will decrease the probability of the second one. And if the human preferred the second response, we maximize the probability of the second trajectory using gradient descent. For this, we usually take the negative log of the probability we want to maximize. The goal is to maximize the probability of the total reward. We actually guide the reward model to assign a higher total reward to the trajectory preferred by the human. And we assign less reward to the trajectory that is not preferred by the human. Now, you can see that we have all three ingredients for a reinforcement learning algorithm. We can train any RL algorithm using this reward model. This was the basic reward model concept to understand how reward models are trained. It generates a reward for each step in the trajectory. You can also generate one reward for the entire trajectory. You can see the details in this paper from 2017, Deep Reinforcement Learning from Human Preferences. Let's study another way of estimating reward function with a single reward value for the entire response. Consider we have two responses as input for our language model. We feed both responses to the reward model to get the reward for each response. The reward model predicts two reward values, one for each response. With this simple loss function, we are forcing the reward model to generate a higher reward for the response preferred by the human. The goal of this negative log is to maximize the inner value, which ranges from 0 to 1. We use the sigmoid activation function. We take the negative log of the output after the activation function. By doing this, the model will predict a higher reward for the response preferred by the human, and it will assign a lower reward to the response not preferred by the human. The reward model will learn to give higher rewards to human-preferred responses, and these rewards will guide the policy network to prioritize human-generated responses. This was a basic overview of the reward model. Let's begin our main proximal policy optimization algorithm. This is the equation we will study. Consider this simple state of two words at time step t, where our goal is to predict the next word's probability distribution using a language model. For simplicity, let's say we have three words for the next token prediction. The next word policy for the current state is simply a softmax distribution over the next tokens. We represent it as our old policy, which we aim to update during training to maximize the reward. Let's say we sampled the first action from this policy, which has a probability of 0.32. Now, we need to determine whether this action is beneficial for us or not. For this purpose, we use the advantage value, which we calculate using the reward model and the value model. The reward model provides the reward for this policy, while the value model determines whether the reward is higher or lower than expected. I have explained in this video how we calculate the advantage value using the reward and value networks, but for simplicity, if the advantage value is positive, it means that the action we took provides more reward than we expected, so it's a good action. Therefore, we should encourage this action. If the advantage value is negative, it means that the action we took provides less reward than we expected, so it's a bad action. Therefore, we should discourage this action. Let's say this is the new policy we want to learn. Initially, it is the same as the old policy, but we will update it using the advantage. The ratio of the new policy to the old policy, along with the advantage function, can be given by this equation. Here, let's say we have a negative advantage, which indicates that this action was not a good one. To discourage this action in the future, we adjust the policy for this action. Remember, our goal is to maximize the output of this equation. We change the current policy to maximize this output. If the advantage value is negative, we adjust the policy to decrease the likelihood of that action in the future. We discourage this action by decreasing its action probability for the given state. If the advantage is positive, it means this is a good action. Then, we should increase the probability of taking this action. By doing this, we encourage this action in the future. You can see that the new policy is updated for the given state. This policy encourages the action taken because its advantage is positive, indicating it's a good action for the given state. This clip function is used to ensure that the new policy does not change too much. This means the ratio of the new policy to the old policy should be clipped within a certain range. This minimum function ensures whether we need the clipped version of the policy ratio or not. But remember, after we change the policy many times, our language model can forget what it has already learned, right? So, for this purpose, we add a reference policy to guide policy updates at every step. This reference policy is taken from a base model with frozen weights, so that our new policy does not diverge too much from its original policy. Let's rewrite the original equation with the KL penalty to prevent excessive divergence from the original policy. This KL divergence penalty will ensure that the reference policy and the new policy remain close to each other. We also have a hyperparameter, beta, associated with the KL divergence term, which controls the strength of the penalty and the degree to which the new policy is allowed to diverge from the reference policy. So, in summary, we had responses. Using human feedback, we categorized those responses. Then we trained a reward model on those responses. After this, we trained our language model policy to prioritize the responses which are preferred by human. But there are some issues with this reward model, which were solved with direct preference optimization algorithm. This paper shows that we do not need to implicitly train a reward model. Instead, we can directly optimize the policy according to human preference. So, let's first understand DeepSeek-R1 0, which uses reinforcement learning to reason without any supervised data for reasoning purposes. Previously, we used to train the reward model and then train the language model policy with reinforcement learning. But we faced issues like reward hacking in the reward model. So, the authors used a rule-based reward for training their thinking model. In the case of math problems with deterministic results, the model provides answers in a specific format, and the results are checked by comparison with actual answer. Similarly, for LeetCode problems, they assign rewards based on test cases. They also assigned rewards for the correct formatting of thinking and answers by the language model. So, if we represent our current policy as the old policy, we sample a list of responses for a query using the language model with this old policy. For each response, we also receive a reward, indicating how accurate the language model's response is for the given query. Now, we calculate the advantage by normalizing all the rewards. You can see that we are subtracting the mean value from each reward. This means that all the advantages less than the mean value will be negative and vice versa. For understanding, consider this normal distribution. You can see that the normalized rewards above the mean value are positive, and all the normalized rewards below the mean value are negative. Remember, when we multiply the advantage by the ratio of the new policy and the old policy, if the advantage is positive, it encourages the new policy to take this action in the future. And if the advantage is negative, it discourages the new policy from taking this action in the future. So, in short, we have a group of responses for a query. We also have their rewards. We normalize those rewards. Now, if the reward for a given response is greater than the mean reward value, it means this reward is a good reward relative to the group of rewards we have. Then, we encourage our language model to generate that response. If the reward for a given response is less than the mean reward, it means this reward is not good relative to the group of rewards we have. Then, we discourage our language model from generating response for this reward value in the future. In short, we are encouraging better than average responses for each group of responses and vice versa. So, this algorithm encourages the good responses and discourages the bad responses relative to the group of responses for a given query. That's why it is known as group relative policy optimization. You can see here that this is averaging the objective term over our entire group. Then, we have the ratio of the new policy over the old policy for every response, and their corresponding advantage values. You can see that the same clipping is applied to it for small policy updates. At the end, we just have the KL divergence penalty to keep the new policy close to our reference model, as we discussed earlier. So, with this group relative policy optimization equation, we try to improve the policy from our current policy every time. Now for the R1, 0 model. We have base model. You can consider it DeepSeek-R1. We train it with group relative policy optimization. But for the R1 model, we first start with some supervised data for chain of thoughts before going for reinforcement learning training.